Hello, this is Yuchao Li. Here I'm going to present our work, Performance Bounds of Model Predictive Control for Unconstrained and Constrained Linear Quadratic Problems and Beyond. This is a joint work with fellow student Aram and three professors, John Ligeras, Kurt Johansson, and Jonas Martensen. As we know, model predictive control is a well-established scheme dealing effectively with state and control constraints. Based upon a model, it predicts how the system evolves into the future in order to facilitate the decision-making at the current stage. The function and constraint designed at the end of predicting horizon, referred to as terminal ingredients, play an important role in performance and analysis. Recently, a framework developed by Basikas couches on the dynamic programming theory and regards MPC as an approximate scheme for solving a functional equation. We leverage on this new framework and investigate how the terminal ingredients affects the performance of MPC. We would like to highlight the difference in perspective in that MPC analyzes the predicted trajectory into the future, that is, it focuses on forward in time and focusing on the trajectory of states, whereas dynamic programming analysis proceeds as the algorithm progress. For example, if we look at the computing shortest path of node 1 to 4 to the destination of node 5, then the dynamic programming starts by setting the values of cost functions of node 1 to 4 into infinity and moving backward and eventually converge to the optimal value. So it's forward in algorithmic iteration and focusing on the functions of states. As we mentioned earlier, that the analysis is couched on the dynamic programming model. So in what follows, we will use the scalar linear quadratic problem as a vehicle to introduce the related concepts. It involves the state space denoted as X and a control constraint set UX. For LQR problem, both of them are real numbers. It involves a system dynamics that maps the product of state and control to state, and the stage cost that maps state and control to a real number. For LQR problem, it's linear system and quadratic cost. We focus on policies that maps state to control such that the control constraints are fulfilled. Its cost function are defined accordingly. And for LQR problem, again, we are focusing on linear feedback. We would like to find the optimal cost function, which is a mapping from state to real numbers, such that, and we would like to compute the optimal policy, such that its cost function equal to the optimal cost. For this class problem and problems well beyond the LQR problem, the optimal cost function fulfills the Bellman's equation, which is optimal cost equal to the stage cost and the optimal cost of next stage minimized over the control constraint set. For the LQR problem, since we know one solution is a quadratic cost, by plugging in this quadratic cost, we obtain this formula. And this is very important because recall that initially we would like to solve the optimization problem that is minimized over the infinite sequence of control. Then this is due to Bellman's equation hold for the optimal cost. This is transformed as solving a fixed point equation. This is a functional equation, involve as many as scalar equations as the number of states. In addition, Bellman's equation also holds for a given policy. There are several classes of classical algorithms for solving Bellman's equation. One is value iteration. It generates a sequence of functions by this iterative formula whereby the J star in Bellman's equation is replaced by the current estimate of J star. For LQR problem, starting with a quadratic cost estimate, this is simplified as a scalar iteration where Fk is the well-known Riccati equation in the scalar form. And in addition, the principle of optimality kind of argument yields that when we minimize over not only one stage, but multiple stages, This can be viewed as minimization over the current control, where the terminal cost is replaced by one step of value iteration starting from k. Another method for solving the problem is policy iteration. It generates a sequence of function, which is a cost function, by performing policy evaluation, that is, solve the cost function for the given policy. And then this is followed by the policy improvement step, whereby we compute an improved policy where J mu k, the cost function of current policy, acts as an estimate of J star. For our LQR problem, starting from a linear feedback that is stable, policy evaluation solve the Lyapunov equation, and the policy improvement step obtain a new linear feedback that fulfill this relation, which is the closed loop system square is the tangent line of Riccati equation evaluated at the previous cost function. Now let's use the dynamic programming model introduced a moment ago to interpret MPC scheme. Consider an MPC scheme for solving a linear quadratic problem, taking this form. The policy mu tilde obtained by the MPC scheme can be considered as performing L minus 2 step of value iteration followed by 1 step of policy iteration. What does that mean? More specifically, minimizing over control that start as next stage to the end of predicting horizon amounts to compute L minus 2 step of value iteration, where K0 is the terminal K as the initial guess of the solution to Bellman's equation. Then the policy mu tilde defined by the MPC, which is then applied to the system, is the linear feedback L tilde, where L tilde fulfill that the closed loop system square is the tangent across the tangent line of the Riccati equation evaluated at the end of the value iteration step. The performance of mu tilde is judged by KL tilde, which is obtained by policy iteration step. Then the cost KL tilde is the approximate solution to Bellman's equation computed via MPC. Similarly, let's consider a constrained problem involving state constraint X hat and control constraint U. Applying MPC with suitably designed terminal cost and terminal constraint, nearly identical interpretation applies. That is, MPC scheme define a policy which amounts to performing L minus 1 step of value iteration followed by 1 step of policy improvement, where K and S collectively act as the initial guess. For this scheme, we have the following result. Let Xi star be the sequence of state under the optimal policy starting from a given X. Then the cost function of the MPC evaluated at X, its optimality gap is bounded by the terminal cost evaluated at the end of predicting horizon under the optimal policy minus the optimal cost at that particular state. So instead of looking at the predicted trajectory, in fact, the performance is bounded by the trajectory under the optimal policy, regardless of the designed K and S. Note that for this problem, since constraint exists, mu star is not linear and J star is not anymore quadratic. Given that in practice, mu star drives the system to zero exponentially fast, so even for large K and K star, the performance bound would be small if XL star is small. Then this performance bound gives us some intuition to design new design approaches. Let's just focus here on the MPC with both terminal constraint and terminal cost. A conventional form of MPC looks like this, where the terminal cost K star solves the associated Riccati equation, and S star has the property that any state within S star is subsequent, the control under the LQR optimal control is feasible, and the subsequent state is also within the same set. So it's forward invariant with respect to the optimal control. The reason for choosing K star as a terminal cost is to have good performance for J mu tilde. But in view of our analysis, this seems not necessary because we can afford to have K that is far away from K star. So based on our insight, a new design could be that to get a good closed loop performance judged by the cost function J mu tilde, it is not crucial for the terminal cost to be K star, which may produce a smaller S star if L star is large. Instead, we may try some K that is related to a small control. As a result, the corresponding terminal set S can be larger than S star. So this is kind of an intuitive argument we employ. Then the new design looks exactly as the previous one. The only difference is that now K solve the associated Lyapunov equation where L is some suboptimal control and a small control perhaps. And since S is larger, the feasible set of the initial state X for the modified MPC is also larger, while the performance should be rather comparable. Let's look at a two-dimensional scalar example. Consider a double integrator with both state and control constraints. We've used a new matrix K designed as solution to the following perturbed Riccati equation where the R term is 50 times of the original R. As a result, K is 6 times of the optimal K measured by their respective norms. And we design terminal set accordingly as the invariant set with respect to some control law. And for the terminal constraint, we can see that for the newly designed terminal cost, the respective terminal constraint set is much larger than the terminal constraint used associated with the optimal cost. And accordingly, the feasible region of MPC is larger, as indicated in this figure, which almost identical to the support of the J star, which is the maximum reachable set. On the other hand, if we look at the performance optimality gap using our newly designed terminal cost and terminal constraint, the optimality gap is the largest part. Actually, is when it's close to the equilibrium point or the origin, and the difference is merely 0.35%. So intuitively, starting from some X star, then the bound is in fact evaluated by X3 star under the optimal policy rather than dependent on K or S. To conclude, we analyzed the performance MPC via the perspective of DP for unconstrained and constrained LQR problem. The insights obtained led to new designs of terminal ingredients with larger feasible regions while costing little in performance. And with that, I would like to conclude and thank you for your time.